Welcome back to our channel. After a short break of about a month occasioned by the 2023 KCSE examination period. Now we are back and it is our pleasure to present 2023 KCSE Chemistry Paper 2, question number 1. Testing on the periodic table, specifically period 3 elements. Welcome and stay on until the end. Remember to subscribe and also to engage the notifications bell so that you are promptly notified when we upload new videos. Now to question number 1. Table 1 gives some properties of elements in period 3 of the periodic table. So we have here elements, of course, sodium all the way to argon. Then we have the atomic numbers 11 to 18, and you can see the atomic sizes. Of course, you can see that the sizes are progressively reducing as we move across. Now, before we answer the questions, it is necessary that we also give the electronic configurations of these elements, beginning with sodium. So because sodium is atomic number 11, the configuration becomes 281. Then we have 282, 283, 284, 285, 286, 287, and 288. These will come in handy as we answer our questions. Now to part A. We are asked to give the formula and the name of that compound which is formed by the reaction between aluminium is here, atomic number 13, configuration 283, meaning valency 3, and sulfur. Sulfur is here, atomic number 16, configuration 286, which means it has valency 2. So because of aluminium having valency 3 and sulfur having valency 2, the formula would actually be Al2S3. Remember, the elements, as we said in Form 1, more or less interchange their valencies as they form the compounds for 1 mark. Name obviously becomes aluminium sulfide, IDE, because this compound is made of only 2 elements, one being aluminium and the other one being sulfur. So the marking point was the name must end in IDE. Now, if a candidate went for aluminium 3 sulfide, you also deserve the mark. Let's move on to part B. And in part B, we are told to explain the variations in the atomic radius of the elements across the period. And as we have mentioned a few moments ago, we can see progressive decrease in the atomic sizes. So the candidate will start with that the atomic sizes, of course, decrease for 1 mark across the period. Then, of course, we don't stop here. We go ahead to explain, because that is what we are asked. We are told to explain the variation. So the explanation is that there is increase in strength of effective nuclear charge for the next mark, making it 2 marks. Now, instead of effective nuclear charge, which was awarded 1 whole mark, another candidate would talk about this decrease being occasioned by increase in number of protons. In number of protons. And this would even be because of increase in nuclear charge without the word effective. So for a candidate who went for this other reason, we would give half mark for increase in number of protons or increase in nuclear charge. But to get now the final half mark, this candidate would go ahead to tell us that this increase in the number of protons leads to stronger pull. So it leads to stronger pull for the next half mark on the outermost electrons. So here, the marking point was effective nuclear charge. But then there is also the other way of expressing it, where a candidate would talk of increase in number of protons for half mark and then stronger pull on outermost electrons for the other half mark. Now to part C, we are told to select an element with the highest ionization energy. And as we know, this must be argon, the one on the extreme left. Of course, the symbol AR would also score the first mark. And then we go ahead and give a reason. The reason is that it has, argon actually, according to our table, has the smallest atomic radius for the next mark. Now, instead of talking about smallest atomic radius, a candidate would also talk of argon having the strongest nuclear attraction. And again, instead of these, another candidate would say that argon is stable, or that argon has stable electronic configuration. But even talking about argon being a noble gas would still earn the mark for giving the reason. Quickly to part D, we are asked to give or write the electronic configuration of phosphorus in phosphorus 3 chloride. So here we were being tested on bonding, and as usual, bonding between phosphorus and chlorine would be as follows. Phosphorus being the central atom, and it would be bonded to 3 chloride atoms covalently, as shown by this dot and cross diagram. So chlorine had 7 electrons on the outermost shell. 1, shown by this dot, would be contributed for bonding, and then the other 6 would remain unbonded. This would happen for every chloride atom. Then, for phosphorus, we had 5 electrons on the outermost shell. Of course, 3 have been used for bonding, so 2 here would remain unbonded. Of course, when we draw this diagram, we don't include the inner electrons. So now the configuration of phosphorus becomes 2, 8 for the inner electrons, and you can see from here the outer shell now has 8 electrons. So the configuration would be 2, 8, 8 for 1 mark. Now, to answer this question, another candidate would look at it from the point of oxidation states. So when we write phosphorus 3-chloride, like what we have written here, the 3 chloride atoms are having an apparent charge of -1 each. And because they are 3, the net contributed by the 3 chloride atoms would be -3. Then phosphorus has to come in to cancel out the -3 apparent charges by having an oxidation state of +3. So if you look at the configuration, which was originally 285, having oxidation state of +3 would mean that our phosphorus is kind of losing 3 electrons. So the other configuration that would be allowed would be 282. And this we get when we look at this compound in terms of the oxidation states of the elements that make it up. Let's proceed now to part C. In part C, we are told to select an element that forms an ion with the smallest ionic radius. So here, the candidate was simply supposed to look at the 3 metals on the left-hand side. They would give ions with the smallest ionic sizes because they form ions through loss of electrons. The nonmetals form ion through gain of electrons, so their ionic radius would actually be bigger. Now, once we have known that the element required here is between sodium, magnesium, and aluminum, now we go for one that loses the highest number of electrons to form an ion, and that is aluminum. Of course, we accept the symbol Al for the first mark. We go ahead to explain that aluminum loses the highest number. Of course, there are 3, so it loses the highest number of electrons. A candidate would even give us the number, which is 3, no big deal. Sodium would lose 1 and magnesium would lose 2. So once aluminum has lost the 3 outer electrons, what happens? Stronger nuclear charge would then pull the remaining electrons, closer to the nucleus. So this explains why the ion of aluminum would actually be the smallest. With that, let's now proceed to part F of the question. In part F, we have been given a second table for question 1. And here we are told that table 2 gives the melting points of some of the elements that we've just discussed in part A to E. So we are provided with the melting point of sodium again 98, magnesium 650, and you can see the melting point of magnesium is higher than that of sodium. Coming to the nonmetals, we have chlorine -101 and argon -189. And again, you can see the melting point of chlorine is higher than that of argon. So the question was asking our candidates that in terms of structure and bonding, the candidates were to explain the differences that have been displayed in the table. Now, beginning with sodium, and magnesium. And we can see that magnesium has a higher melting point than sodium. The candidate was not supposed to repeat this trend because it is visible in the table. So here we want to go ahead and explain why the melting point of magnesium is higher than that of sodium. And we know that magnesium has more delocalized electrons in its structure. Remember, we've been told to explain these in terms of structure and bonding. So because it has more delocalized electrons in its structure than sodium, it has stronger metallic bond. Of course, this was very well explained in Form 2, that strength of the metallic bond depends on the number of delocalized electrons. The more they are, the stronger the bonds. The less stronger the bond. So more delocalized electrons would earn 1 whole mark, and stronger metallic bond another mark. Candidate, remember, here we didn't have to show the trend. It's already indicated in the table. I know many of you would start with magnesium has a higher melting point and you expect any marks. We were not awarding that. Reason is the table is already having that trend. Let's now look at chlorine and argon. Again, we can see the melting point of chlorine is higher. Don't tell us that. Go straight to the reason. So we know that chlorine is diatomic, while argon is monoatomic. This would give the candidate the first mark, giving the differences. Then we go ahead and explain that therefore chlorine has more van der Waals forces as compared to argon. Now, I know many are wondering, why am I using the word more? More is chemically correct. But for those candidates who used the word stronger van der Waals forces, we also didn't deny you the mark, but please take note that talking about chlorine having more van der Waals forces than argon is more chemically correct than comparing the strength of the van der Waals force. Remember, all van der Waals forces are weak. There is none which is stronger. So we've been using this term stronger van der Waals forces even in class, but get to know it is chemically incorrect. And with that, we've come to the end of our short video where we have taken you through the expected responses to the questions that came from the topic, the periodic table, as tested in the year 2023 KCSE. Thank you so much for being with us up to now.